enter. Okay, so here's the deal. If you have a poker, it's like room temperature, but if you put that poker into a fire, what you're going to do is actually, that poker will begin to glow hot. If you take that hot poker out and hold it up, it is actually going to ooze energy, okay? There's this concept called black body radiation, the radiation that is being oozed by an object like that. And we can create what we call black body radiation curves. And so actually, these are 4 radiation curves from 4 different objects. Hopefully you can see the blue, the yellow, the red, and actually the black curve here. Okay, so we have the blue, yellow, red, and a little black curve. Notice that kind of like we looked at before with regard to spectra, along the x-axis we have different wavelengths. Only just a sliver of it is the cousin visible. Of course, over here we have shorter, more energetic, shorter wavelengths, more energetic energies. Over here we have longer wavelengths, less energetic energies. So those curves are like fingerprints telling us, those black body radiation curves tell us the temperature of those objects. For instance, that blue one is a hot star. And it's just telling us the surface of that star, what its temperature is. Okay, and it's running 15,000 Kelvin. Now, when we talk about stars, and maybe intuitively you know, when we get into the center of the star, it's a lot hotter than that. But 15,000 Kelvin, that's pretty warm. Okay, the next curve actually is kind of what a typical G-type star, as ours, would be with regard to its surface temperature. Almost 6,000 Kelvin, 5,800 Kelvin, degrees Kelvin, or Kelvin units, is the surface, the temperature of the surface of our sun. The red line is a cooler star, okay, 3,000. So we have 15,000, about 6,000, and 3,000 Kelvin is those 3 objects. So a few things. Notice that actually the peaks, and I usually would talk about a lambda max. So up here, this peak up here, this is actually corresponds to a peak wavelength. So lambda is the symbol for wavelength, lambda max, the peak. Over here, this is our lambda max for our sun. Okay, scooted clear over here, this is lambda max for that cooler star, 3,000 Kelvin. So when I talk about Wien and Stefan Boltzmann's law here in a minute, that actually is one of the characteristics of gauging the temperature of an object. Is you'll see that its entire curve will go, the warmer it is, the hotter it is, you know, the peak is going to be here at the shorter wavelength. Okay, the cooler it is, the peak is going to be over here at the longer wavelength. So the other thing is to point out, and this is the other aspect of this law that and it makes sense, is think of this as intensity. So the higher up on the y-axis, the more intense it is at that wavelength. So can you see this hottest star, 15,000 Kelvin, that not only is its maximum over here at the shortest wavelength, but it's got the most intensity at all the wavelengths. And that's characteristics of hot objects. Okay, the coolest star, okay, notice that it's got the squattiest intensity, and it is kind of skewed over here. It peaks out over here at the longest wavelength. Well, there's one more black body radiation curve I haven't shown, okay, and that is humans. So if you were to take the black body radiation curve coming from a typical person, okay, it is oozing, we are oozing that little signature down there. Isn't that cool? A little bit of thermal energy. So just in general, to kind of summarize these, again, Wien and Stefan Boltzmann's law, basically, the hotter an object, okay, the hotter an object, like we saw that hot star, 15,000 Kelvin, the more light it will emit at all frequencies. Okay, so the higher up the curve is, okay, the cooler the object, the less energy it will emit at all at frequencies. The other thing is the hotter the object, again, this star right here, it will emit photons with a higher average energy. Now here's where I probably can add to this. In other words, i.e., okay, it will emit photons, i.e. at a higher average energy, i.e. shorter wavelength. I hope that makes sense.